So let's go now to the last part of today's lecture, which is about functions. A reminder again of what functions are, in particular also what the domain and the range of function is. So let's have a look first of all at some notational questions. So in particular the notation of intervals. So an interval is basically a section of the real number, of the numbers, of the number line, part of the number line. So what we want to sort of distinguish is an interval of all the numbers between A and B, where A and B themselves, the endpoints, are not part of the interval. That's what we call an open interval. So we see down there on the number line, if we look at the interval, if we want to sort of denote all the numbers between -1 and 2, but excluding -1 and 2 themselves. So we look any number between -1 and 2, but not -1 and 2, the boundaries themselves. Well, that's actually an example of this. Any x between the boundary -1 in our case and the boundary 2 on the right hand side. That's called an open interval because both boundaries are not there. And that's denoted by these square brackets. So this is the interval between -1 and 2, but -1 and 2 themselves are not allowed, are not included. So if you want to denote all values of x for an interval between A and B, where you actually allow A and B themselves also to be part, to be allowed values, well, there's an example over here. So any number between 3 and 4 and 3 and 4, the boundaries themselves, are actually also okay. And this is called a closed interval. So any number between some A and B, in our case 3 and 4, and x is between those or actually equal to those boundaries. So x is between 3 and 4 or equal to 3 or equal to 4. So that's called a closed interval, and we denote that with these square brackets over here. So it will be the square brackets interval 3, 4 will mean all the numbers between 3 and 4 themselves included, a closed interval. Now we can mix those up, of course, and it will not be surprising. So you might want to include one boundary, yes, in this case B, but not the boundary B or boundary A. Then we would have a half open interval where B is included, A is excluded, or vice versa. If we want to include A, we put a square bracket on the left-hand side, A is included, but we would not allow B in this interval. That's again called half open, but now with the round bracket and the right hand side. So an example again would be this particular interval over here. The red bit over here means, you know, any number between -4 and -2 is allowed. -4, any number between -4 and -2. -4 itself is okay too, square bracket, a dot over here. But we don't want to allow -2 itself. So on the -2 side, this thing is actually open and not closed. So that's just some notation and terminology that we need to use in order to denote regions basically on the number line, or intervals on the number line as they are called. So with that notation in hand, we can have a look now at functions. Oh, sorry, there's one thing that I need to extend this into. So far I looked at bounded intervals, right? It's a bit bounded between one left-hand bound, the A, and the other, the right-hand bound, B. But we actually also want to look at potentially at unbounded interval. And that might be, you know, any number that's bigger than A, but how big it will be, I don't care. It can be as big as we wish. So it might range from A all the way to infinity. So this funny 8 figure, but on its side, that means infinity. So this particular expression from A to infinity, and note for infinity you also call this an open interval because infinity itself, it's not a real number, right? It's just a notation. It means all numbers x which are bigger than or equal to A. And similarly, if we want all numbers which are smaller than B, but not include B either, so it's going to be open on the B side, we have a round bracket over here, all the way down to -infinity, so as small as you would like, and again there's an open bracket here. So these are unbounded intervals in the sense that they have no bound, at least on one side. They're infinitely long. Right, let's go to functions and the domains and ranges of functions. So a function f, what's that? Well, that means, if I give you a number x in the domain, so that's just a set of allowed values for x, then what f does, the function does, is compute some new number out of this. Basically a black box. I put x in and f then tells me, oh, you get some particular output, f of x. So this d of f is called, again, the domain of f. So it gives all the allowed inputs that we can put into this function. So you can see here actually a graph of some f over some domain for all possible x's that we might allow. So here you see this domain is denoted by this thick line. Those will be all the x's that we will allow for x that we want to look at. That's the domain. So what's the range? Well, the range is all the possible resulting values. So here, so what values does this function f, depicted here in this graph, send each of these x's in this domain to? So what y values will occur? Well, that will be the range of this function f. Okay, that's some terminology again. Let's have a look again what this means. So for an example, this function x might be given as f of x equals, in this case, x squared plus x minus 9. So that's a rule that allows you to assign a new value to any x that you put in. So how would you do that? Well, suppose x equals 2, and we would like to know the function value for the input x equals 2. We would just put in 2 everywhere where we see x. So that means we put a 2 here, 2 squared, which is 4, plus x, so plus 2, 4 plus 2 is 6, minus 9 gives us, of course, minus 3. So the output for this function, if we have as an input x equals 2, the output, or the y, if you wish, is going to be minus 3. So similarly, if we use minus 4 as the input, x equals minus 4, put in minus 4. So what do we need to do? Put in minus 4 at the x position, so minus 4 squared. How much is that? Well, it's actually 16. Right, minus 4 times minus 4 is plus 16. Plus x is plus minus 4. So 16 minus 4 leaves 12. Minus this 9 over here, 12 minus 9. Outcome here is plus 3, just 3. So f, when operating on the value minus 4, gives us an output 3. So note that we allow this f to work on whatever we put in. So if you put in something more complicated, over here for instance, if we put in not x but x plus 1, then we just follow the same rules, but now operate those on x plus 1. So if I put in x plus 1, what do I need to do? I have to square this input, and the square here. So in this case, the input is x plus 1, so I have to square x plus 1. Hence this x plus 1 squared. I have to add the input to that, so plus x plus 1, and then I have to subtract its concept, minus 9. Well, now I need to work this out. The first bit gives us x squared plus 2x plus 1. I have to add to that x plus 1, then I have to subtract 9, and if you do that, simplify that expression, you of course find x squared plus 3x minus 7. So this is how it works. You just operate with the rules that the f is given by, the function is given by, on the stuff that you put into this function. So here's a mistake that I'm sure you will never make. You don't want to just say, oh, it's actually the original function as if operated by x, and then somehow adding this one. But perhaps the better thing is just to forget about this line. Just know what we just did. You operate on what you put in. So let's practice this a bit for an example, actually. So here's an example question. And the question here is, suppose we have a function which is defined as, well, given an input x, what I want to do is, I want to multiply it by 3x. And I want to subtract x to the power 3, so the input to the power 3. So the function is 3x minus x to the power 3. And now the question here is, apparently, can we prove that if you operate this function on the number minus x, then the output for this particular case is actually going to be minus f of x. So let's see whether we can prove this. So it's here on the slide actually, but let's just do it on paper to see how it works in detail. So there we go. So we have this function f of x, which was defined as 3x minus x cubed. And we're asked, if this is the function, what then is the f of minus x? So how do we do that? Well, we have to plug in minus x everywhere where we see the input. So that's going to be 3 times minus x, first thing, minus, well, again, we have to plug in minus x where we see the input. It's going to be minus x to the power 3. So let's simplify that. The first bit, of course, 3 times minus x is minus 3x. For the second bit, minus x to the 3, that's actually minus 1 times x to the power 3. Or in other words, minus 3x minus 1 to the power 3, which is minus 1, times x to the power 3. And now we're done, because if you just cancel those brackets, the minus times the minus gives a plus. So we get plus 1 times x to the power 3. And indeed, so the original question you remember is, can we prove that for this particular function f operating on minus x equals to minus f of x? Well, is that true? Yeah, that's true. So minus f of x will be minus 3x plus x to the power 3, or x cubed. So for this particular function, this is true. Beware, this is of course not true for any function. So these functions which have this are rather special. Okay, so let's go back to the slides. So the same computation is done here, so we just did that. So the next thing that we need to look at a bit more closely is again this thing domain. So remember again, domain means all the allowed values that you want to put into your function f. So let's take some f, consider some function f. We could say, well, I'm only interested in some particular sub-region, some particular interval of x's, but there's one very special sub-region which is called the natural domain of a function. So the natural domain of f, or df, that's all the possible allowed values, so the values x for which fx is defined. So here we have an example where the domain is given explicitly. So fx is x squared, and this particular function x squared plus 3x. For some reason, we are only interested in the values x between 2, 7. So any number between 2 on the left-hand side, or 7 on the right-hand side, and 2 and 7 themselves are included. Remember, this is a closed interval, so including the boundaries. But you might sort of counter to this example, well, why don't you want to look at x equals 0? Because that's definitely not in that interval. It's not between 2 and 7. This is not very natural. No, indeed, the natural domain is much larger. Actually, we could put in any value of x for this particular function, and there would be no problem in computing that. So the natural domain for this particular function would be actually any number, any real number. So if the domain for a function is not given in an exercise, typically what we mean is the natural domain, any allowed number. So for this, again, for this particular function, any number, any real numbers allowed, well, that's not the same for any function. So consider, for instance, the function fx is the square root of x. That's also a function, but of course, in a square root, you cannot actually plug in any negative numbers. So the natural domain in this case of this function, the square root of x, is just all the positive numbers, including 0, right? 0 is okay, but negative numbers are not okay. So the natural domain is any number between basically 0, including 0, up to infinity. So anything bigger than 0 goes, but negative numbers are not allowed. So how do you determine the natural domain of a function? Well, you just have to verify what are all the conditions that need to be satisfied by the values of x that I plug in so that actually this particular function is defined, is allowed. So if you have fractions, so a fraction with something in the denominator, and a different way of writing a fraction is to write it with a negative exponent, if you remember. I'll come back to that actually on paper. We know that if there's a denominator, it should never be equal to 0. So in this case, there will be a condition saying, well, this particular function with a denominator that's not going to define for those values of x for which actually the denominator is going to be equal to 0. And similarly, like we just had for a square root, if you have a square root, then we can plug in lots of numbers, but it should not be negative. We cannot have negative numbers under the square root. So again, this limits the potential values of x that we can plug into this particular formula. So it limits how big the natural domain of this particular function is going to be. We'll have an example next week of logarithms where again there will be limits on what potential numbers you can take the logarithm of, and that's going to again restrict what the natural domain is going to be. So the approach to finding the natural domain of a function is, well, first determine all the conditions that you find. If you have a fraction, you don't want 0 denominators. If you have a square root in this function, well, we don't want negative expressions under this square root, and similarly again for logarithms. Once we have all these conditions, then we combine those conditions. So let's have a look at an example. So the example here is the natural domain of this function g over here, g as a function of the variable t. So it's given as the square root of this particular expression of t plus 3t plus 6 to the power minus 1. So I'll get back to that, what that means again, plus 5 times t. So let's do that on paper. There we go. So let me write again this function g of t is the square root of t plus 6 times minus 2t plus 7, the square root, plus 3t plus 6 to the minus 1 plus 5t. So this has 3 parts. Let me now emphasize this particular bit here. So what is this notation? Something to the power minus 1 just means 1 divided by that something. So in particular, if I were to look at x to the power minus 1, that's essentially just a different way of writing 1 divided by x. So that's what a negative exponent means. Similarly, x to the power minus 2, that's just a different way of writing 1 divided by x squared. And for future use, we also might sometimes encounter stuff like x to, say, the power a half. So what would that be? Think of it, x to the power a half. And that's a different way of writing the square root of x. And if you want to go further, x to the power a third, that would then of course be, sure you know this and figure this out, it will be the cube root of x. Okay, so that's what these negative powers means 1 divided by, or the thing itself. If you have these fractional powers, we are looking at particular roots, either the square root or the cube root in this case, and what you wish. So once we see here this 3t plus 6 to the power minus 1, what does it mean? It just means, this thing actually means it's 1 divided by 3t plus 6. Different way of writing that same expression that we'll actually encounter a lot in text. 3t plus 6. So if you don't remember this quite, have a look at the slides actually at the end of this slideshow, because there's some an appendix basically that outlines these rules once again. So let's get back to the question that we were looking into. So I have this particular function g of t. It has these three different components, and we were asked what's the natural domain of this function g. So again, what does that mean? It means what values of t are actually allowed here. What values of t can we plug into this function g so that we get basically a defined function. So there's two particular worries that we have two conditions that we have to look into. One thing is, well, we have here a square root. And you remember, if we have a square root, we can't have that the expression below this square root is going to be negative, right? So the first condition, condition 1, t plus 6 times minus 2t plus 7. So that's the stuff that's under the square root. We can't have this to be negative, or in other words, we want this to be positive or equal to 0. Then there will be a second condition, we'll look in later. 3t plus 6 to the power minus 1. Well, we just covered that this actually is a shorthand way of writing 1 divided by 3t plus 6. But again, yeah, there's going to be a condition. We don't want this to be 0, right? So 3t plus 6 is not allowed to be 0, because then we're telling this function to divide by 0, which is of course not allowed. So that's condition 2. Condition 2. So those are the two conditions. So what are what's going to be the domain, the natural domain of this function g? It's all the values of t that satisfy these two conditions. So let's figure out which values of t that actually is. So the first condition here, well, what is that? That's an inequality, right? So we looked into how to solve for inequalities. Well, the nice part here is it has already been factored. So we see two factors, t plus 6 and minus 2t plus 7. And you recall how are we going to deal with an inequality by looking at the sign diagram. So what was the sign diagram? We look at the number line and we first figure out what are the special values here. Special values is those values at which either one factor or the other factor is going to be 0. So when is the first factor going to be 0 for which values of t? Well, that's going to be, of course, for t equals minus 6. That's going to be an important number. And the second important number is where the second factor is going to be 0. And if you look a bit at this, is going to be the number 3.5. So those are the special values that we need to distinguish. So we now look at how these two factors, t plus 6 is the first factor, minus 2t plus 7 is the second factor, how those behave on this number line. Well, the first one, t plus 6. If t is below minus 6, then t plus 6 is going to be below 0. So here we have the dashed line, remember, signifying that this thing is going to be negative. At the minus 6, of course, this thing is going to be 0. That's what quite was special. And for any value above minus 6, this expression, this factor t plus 6, is going to be positive. So that was the drawn line, right? So that's first factor. Second factor is this minus 2t plus 7. It's going to be 0 at this special value here. How is it behaving for other values? Well, if you think a bit about this, at the left-hand side for smaller numbers, well, because with this minus 2, this whole thing is going to be bigger. So here we have all positive values for this expression. Whereas if t is bigger than 3.5, this expression is going to be negative. So this is the negatives. So now we know on the whole number line basically how this expression t plus 6 times minus 2t plus 7, how that behaves. Now we can combine that to look at the whole expression t plus 6 times minus t plus 7 is going to be 0 when either of these subfactors is going to be 0, right? Here and here. On the left-hand side, for even smaller numbers, t smaller than minus 6, we will have a negative factor, this is the first one, times a positive factor, the second one. So negative times positive is going to be negative. In between these two zeros, between minus 6 and 3.5, we have two positive factors. So the product of those two positive factors is going to be positive itself. And if you look further to the right hand side, so for values t bigger than 3.5, we have a positive first factor times the negative second factor. It's going to be minus. So if we are trying to figure out, for what values of t is this condition going to hold, so when is this expression going to be bigger than or equal to 0, the first condition tells us, well, we have to be actually in this region of the number line. Any number between, so condition 1 basically says t should be in any number between minus 6 and 3.5. Or a different way of writing this, t should be bigger or equal to minus 6, but smaller than or equal to 3.5. Same thing. This is a closed interval, right? Remember? So this is condition 1. Let's now look at condition 2 over here. So let me just do that the right hand side over here. Condition 2 is actually simpler, right? So we don't want 3t plus 6 to be equal to 0. So let's solve 3t plus 6 equals 0. Of course, this is easily solved by saying, oh, that actually it's going to be 3t equals minus 6, or t equals minus 6 divided by 3 is minus 2. So the condition 2 is going to be, well, we don't want this thing to be 0, so we don't want t, we don't allow t to be equal to minus 2. So now we are where we want to be because we have solved both conditions. T should be in between minus 6 and 3.5. That was by this first condition relating to this square root. But t should not be minus 2, which is actually in this region, right? So the result, the natural domain of this function g, is actually any number t which is, well, first of all, between minus 6, because of this first condition, and minus 2. Minus 2 itself is not allowed because of the second condition. And, or I should say, t is bigger than minus 2, but t should be smaller than or equal to 3.5. So the t can be either in this region or in this region. So this is here I sort of denoted the natural domain using these this particular notation. If you use the interval notation, the way to describe this would be t is in, or it's an element of, we sometimes say it's in, first bit minus 6, including minus 6, so the square bracket, up to minus 2, round bracket over there because minus 2 itself is not allowed, so it's open on this side, combined with, and this u kind of symbol means combined with, the numbers between minus 2 and 3.5. And that's again, so and this thing is the natural domain of g, t of g. Okay, so let's go back to the slides now. So here we are. on the slide. Here we see this first condition again, t plus 6 times minus 2t plus 7 should be bigger than or equal to 0 because of this square root. We solve that with this sign diagram. So you see this area down there which signifies which values of t actually solve that condition at inequality. Second condition was this value that t should not be because of this fraction 3t plus 6, so t should not be equal to minus 2. That's also what we found. So the final result, if we have to combine those two conditions, so the interval, or the domain of this, the natural domain of this function is this combination or union, as it's called, of these two intervals, the half open interval of all the numbers between minus 6 included and minus 2 not included, and minus 2 any number t between minus 2 and 3.5, where 3.5 again is included. So that's what we just found. The final example, also look at the range. So just as a simple example, basically showing what the range means. So remember, range means all the outputs that a function could give, given the inputs that are allowed that are in the domain. So to just give an example here, let's consider this function h of x. So let's look at that. It's square root of 2x plus 4. That's the function h of x. What is its domain? Well, domain is any number x bigger or equal to minus 2, and that's actually the natural domain of this function a, so you can check. And the question is the number 4 actually in the range? So is that a possible outcome of this function? So how do we verify that? Well, let's check. What does it mean? Is there any x for which, if we plug it into this function, square root of 2x plus 4, that we get 4? That's the question. Well, let's try to solve that by just solving this equation. Well, let's square it. Same thing, 2x plus 4 equal, it's the square root of the square root. And on the right hand side, we also take the square. 4 squared is 60. 2x plus 4 is 60. So if you work that out, you'll find, oh, actually, if you plug in x equals 6, then the square root indeed is going to be 4. So 4 is indeed a possible outcome, namely for the input x equals 6. So 4 indeed belongs to the range of this function h. So this is it for today. What you can find in the slide pack, again, is a solution to one of the exercises that I left for homework. So you can have a look at that as well. And then there will also be an appendix having the various rules for these fractional and also negative powers that I just explained briefly on paper as well. So good luck with those and in preparing for the first tutorials. So have a look at the schedule, which gives you some information about what exercises will be done in the tutorial. Have a look at the videos of some of these exercises before you go to the online tutorial on Friday, and then practice. Basically, practice is the mantra for mathematics in general. Practice these different exercises and ask your questions in the tutorial. And then we'll see each other next week again. Bye bye.